of my classes. Today, we're going to continue the path that we started on Monday, which was going through the basics of quantum machine learning, and some basic theory for representation and group theory, and how to use those results to see if we can classically simulate some quantum algorithms that don't have barren plateaus. Yesterday, we focused on this Hamiltonian variational ansatz based on an Ising model. And we saw that this guy, which worked really well for VQE, and it didn't have barren plateaus, it's because it's effectively living in a small subspace of a couple of Majoranas. And we saw how to do the simulation from start to end. If you have access to measurements from a quantum computer, where you take your initial state, and you measure all the elements in pairs of Majorana. So in the language of yesterday, all the elements in B2. And this allowed us for this simulation for all parameter points, and we're going to review again the different notions of simulability. I'm going to sound like a broken record, so we're going to go through a few of the slides that we've already gone through a couple of times. But today we're going to take a look at quantum convolutional neural networks, and we'll see that the pipeline here is effectively the same, but the quantization is going to be effective, and we'll see what that means. So again, what we're trying to show is that QCNNs should not be implemented in this model where we put our data into a quantum computer, we send them through a QCNN, a parameterized circuit that does this optimization loop. If you don't know what a QCNN is, we're going to get to that in just a second. And the steps are again going to be the same. We're going to identify the subspace where the model is gonna live in. We're going to see what is the set of measurements that we need to do in our quantum data. We're going to study what type of classical simulability, and again, we're going to get to our dequantization of this model. Again, different notions of simulability. What we're going to start to see is that we can do the simulation for QCNNs fairly easily on average. And this is something that we can try to prove. It's going to be quite a bit of math. If I can get to the point where we can actually prove this analytically in the blackboard, I'm going to try to give you the tools so that you can do the last few steps on your own. Of course, we would like to have something like what we did for transverse field Ising model, where we could simulate the loss function for all the set of points. But for this particular case, the quantum convolutional neural network, we're going to see that we're going to be able to do some effective simulation in the subspace where our model lives. And we're going to be able to find solutions that are as good as the ones that you would get if you were running the whole thing on a quantum computer. So we're kind of like going to skip this, and we're going to connect the top to the bottom. So this is our goal for today. So who here is familiar with quantum convolutional neural networks or knows what they are? Okay, that is maybe about a third of people, so let me try to recall them. First of all, disclaimer, if you know about classical convolutional neural networks, who knows about them? Yes, quantum have nothing to do with them. There is no convolution. I don't even think they're neural networks. It's just marketing. So yes, the name convolutional has a very precise meaning in mathematics. To do a convolution is a very precise mathematical operation that is not happening here. That much I can guarantee. Why do they have that name? I don't know. I think it's just because classical convolutional neural networks have this idea of taking your data and just running filters through it to do the convolution, try to reduce the feature space dimension as you go through the different filters. And this is something similar to what these circuits are doing. So in the vanilla quantum convolutional neural network, and you're going to see me struggle with this, I say quantum so much that I'm no longer able to just refer to classical convolutional neural networks. I always say quantum, even if I refer to classical. So my brain is just wired that way now. I've talked about this architecture so much. So in this quantum convolutional neural network, you're going to start with some input states, and then what you're going to do is that you're going to send it through a sequence of parameterized unitaries. In the easiest way, they're going to, again, have this kind of like brick-like structure where parameterized gates are acting on pairs of neighboring qubits. Why do we do this? It's easy to implement on devices with linear connectivity. And then you go through what people call pooling layers. The idea of the pooling layers is to reduce the dimensionality of your feature space by either tracing out or measuring qubits. So in this architecture, here I'm showing you one where you do measurements and you condition one unitary operation on those measurement outcomes. But in principle, you could do something simpler, like just throw away some qubits. You just forget about them. And you keep doing this for a sequence of layers, and eventually you will end up with 1 or 2 qubits of interest. Something interesting to see is that in most of those architectures, you're always tracing about half of your qubits, or floor half if you don't have a multiple of 2. So this means that this architecture is naturally shallow. If you're starting with a number of qubits that is a multiple of 2, you can have at most log n layers, because after that, you're out of qubits, right? So they're naturally very, very shallow, and this is something that people quite liked. Today, we're going to focus on quantum convolutional neural networks that don't have intermediate measurements. So we're not going to have measurements and control unitaries. And we're not going to talk about those. We're going to talk about things that look like this, where you do tracing out. Now, you might be saying, OK, but this is a more restrictive class than this. But for all intents and purposes, in our experiences of training quantum convolutional neural networks, these work much better than this. So you might want to add this just to make our proofs harder. But my reason is why? This works already better. So why complicate your life so much? Because this is already capable of solving the problem. Something interesting to note is that imagine that here I'm just tracing out qubits. There's no measurement. If I take a measurement operator and I do the backward slide cone, and I just try to see what are the input qubits that are going to be affected if I Heisenberg evolve this measurement operator. What is the answer? Is it like a hardware efficient ansatz, or is it just a subset of qubits? You can just take this. So something interesting about this architecture, and I don't know if it's blatantly obvious or not, is that all the qubits are in the Heisenberg evolved light cone of the measurement. So that means that we're not going to be able to get away with something as easily as just doing tomography on a subset of qubits, because here our measurement looks at all of the qubits. For people that know tensor networks, this kind of looks like a Mera in reverse. This doesn't mean that this is a Mera in reverse, because the whole point is that this input state can be arbitrary. And when we put out our paper on like quantum convolutional neural networks are simulable, people were like, oh, it's obvious, it's Mera. And I'm like, yeah, but this is simulable via Mera if your input state has low bond dimension. If I give you an arbitrary input state, this is no longer simulable by Mera. So I just want to make that because it's a pet peeve of mine that people always say like, trivially dequantizable via Mera. And I'm like, no, that is not true. So I'm sorry that you had to hear me go through that rant. Then something that people like about this architecture is that we were actually able to rigorously prove that they don't have barren plateaus. We can also do some numerics. If you correlate and uncorrelate parameters, this is not exponentially decaying. So this was really nice because they're naturally shallow, they don't have barren plateaus, they actually work quite well. And people thought, let's use this for pretty much everything where a classical convolutional neural network is used. Let's put quantum in it and try to get some advantage. But today we're going to try to see that this is actually not so much. And also we're going to try to rederive in a different way the proof of our paper where we prove absence of barren plateaus, which was like 20 pages. You can actually do it in like 4 or 5 lines if you know the right tools, which means that when we derived that proof, we didn't know Weingarten calculus, which is what we're going to teach today. So we just had to brute force our way through the proof, but there's a much more simple and elegant way. So I think this is pretty much all that I wanted to say with the Blackboard, with the slides. Now it's going to be Blackboard time, and just like before, I'm going to put a cheat sheet here that we're going to use throughout the rest of the talk. All right, so what is the goal today? The goal today is we're going to be interested in computing things that are going to look like expectation values when unitaries are sampled from some group of quantities that look like our quantity of interest, U, rho, U dagger, O, to some power T. This is what we're going to try to do today, analyze these quantities. So this we're already familiar with. This is kind of like the type of loss functions that we said our quantum models are going to be based on. And we also have this power T here. So we're just taking this, putting it to some power T. We're going to see why this is going to be important in a second. But let me first focus on this. We have an expectation value over unitaries sampled from some group. Usually, when I give you a group, I could have also said, I'm going to sample unitaries from a set that is equipped with a probability distribution. So I can just give you probability of unitary U and unitary U, and just unitaries that belong to this set right here. And this guy right here, if this would be a discrete probability, it would be nothing more than the summation when U belongs to this set of probability of U, trace, U, row, U dagger, O to the tth power. So in discrete, it doesn't look too bad. It just means take your quantity, evaluate it at the different unitaries in your set, get to the tth power, multiply by the probability, and make a summation. Whenever this is continuous, you just replace by an integral. Let me still call this S. And we're going to have this integral over du, probability of U, trace of U, row, U dagger O, to the tth power. So whenever I talk about expectation values, I'm going to be talking about integrals that will take this form. But here you note that I'm not explicitly defining a probability distribution because I'm going to take the simplest probability distribution, which is you have a group, let me sample unitaries uniformly. So we will just assume that whenever we have something like this means like uniform sampling of the unitaries over the group. Now, the uniform measure, which I'm going to henceforth assume that I have uniform sampling over a group, so this S is just going to become a group. And I'm going to denote the uniform measure over the group in this way. And this fellow right here is simply called the Haar measure. If you've heard about this, or maybe you've encountered this term before. It has quite a bit of meaning whenever you have structures over which you're sampling uniformly. For our intents and purposes, it just means we will sample uniformly over a group. Just take as uniformly as possible the unitaries over the group. And the Haar measure has some really nice properties, which I'm going to try to write here. This is going to be, again, our Blackboard, where we're going to try to write the information that we're going to be focusing on. The first property of the Haar measure is that it's normalized. And if you think about it as a probability distribution, just kind of like this step right here, that should make sense. So we have this one. Haar measure is technically not uniquely defined. You can define different measures, but they're going to be proportional to this up to a constant. So for our purpose, we're going to take the Haar measure as the one that is normalized. Then it has the property that it is what people call left and right invariant. So that means that if I'm integrating a function that depends on U, and then I give you some v that belongs to the group, then this equality is going to be satisfied. Is it obvious why this should be the case? If you think about a group, I'm taking a unitary that belongs to this group. Here, we already know that the property of a group is that it's closed, so U times V also belongs to the group. So all that I'm doing here is a relabeling of the index, because if I'm sampling all the unitaries uniformly, and I multiply them all by V, the uniform sampling should be exactly the same. So this is just a property of the fact that we have a group and we're uniformly sampling over it. These two are going to be fundamental properties, and we're going to also have them up there on the top. So this is something that is going to be very useful. Now, once we've assumed that we want to do this integral, oh, I'm missing a t here, we can try to explicitly compute this. And just like before, we're going to start assuming that we have some generic group G, and we're going to try to do the whole calculation and then specify special cases. Something that I should be doing, just to be consistent with yesterday, and I'm sorry about this, we have representations of groups. Let me actually do this again. And let's say that we're going to have G is a group, H is a Hilbert space. I always say that one should define the spaces one where one is working on, and I forgot to do exactly the same thing yesterday. And we have R that takes from G to the set of invertible matrices on H. So we're going to be uniformly sampling over this representation. Now, how do we go about computing this, and why is this important? The first thing is let's try to understand why do we care about computing this kind of quantities, especially in the context of barren plateaus. You're going to see that this type of integrals are very important. Because one question in barren plateaus that we care for is our loss function going to be exponentially concentrated? If I sample unitaries from my group, which could be equivalent to different random initializations under some mild assumptions, what is that quantity going to look like? So in general, I'm going to be interested in quantities like what is the variance over unitaries of this loss function that we defined yesterday. If we expand this, we know that this is the expectation value over U of the trace of U rho U dagger O squared minus the expectation value over U of trace U rho U dagger O, and all of this is squared. So in our calculations of concentrations, this is precisely the type of things that we need to do. We need to compute expectation values over this kind of loss functions. And if you haven't really connected why this is related to concentration of the loss function, I think it's kind of natural to say, how much is this going to be oscillating around its mean? But you can also think about this from a probabilistic statement, which if I ask the question, what is the probability that this guy right here, for some unitary, deviates from its mean by more than a quantity C, where C is larger or equal than 0. This is upper bounded via Chebyshev's inequality by this guy right here. So this is really nice because it truly connects. If I randomly sample a unitary, what is the probability that I deviate by this quantity? If C is order 1, maybe you want like 2/3 probability, but this is exponentially small. Your probability of deviating from the mean is exponentially small. So yes, computing this type of quantities is going to be at the very heart of understanding barren plateaus, their existence and their absence. So the first thing that I'm going to do now is we're going to start with this equation right here, which I am going to, let's just do this. And let me do the first equality. Would you believe me if I tell you that this is true? The trace of A tensor B is the trace of A times the trace of B. Cool. So that means that we can write this as the integral of the trace of U tensor T rho tensor T U dagger tensor T O tensor T, where we just applied that equation T times, right? Clear for everyone? Okay. Then integrals, if you think about summations and you think about the trace is linear. So I can just take this and put it inside of the trace. So this is equal to the trace of the integral G d mu U of U tensor T rho tensor T U dagger tensor T O tensor T. And now we see that the integral that we wanted to compute, we don't have to work at the scalar level, because this is a number, right? It's the trace. We can work on it at the operator level, and this is a little bit more fundamental. And this thing right here, it's so important that it even has its own name, and people call this the teeth-fold twirl operator. Which I'm going to define here. I'm going to denote as tau of G of order T. Let's do it correctly. R of G is going to be equal to the, it's a super operator, so it takes an object, more specifically, it doesn't just take an object. We can define what its action is going to take a bounded operator on H tensor T, and is going to return a bounded operator on H tensor T. And its action is simply going to be given by this thing right here. So this is really nice because now Twirl starts appearing. Maybe you've heard about Pauli twirling or twirling in the context of randomized benchmarking, and it's just this basic idea here. And the thing is that now we want to explicitly compute the action of this twirl. We want to see where does it take an operator, and how can we know exactly what it's going to return. So from now on, let me just focus on the twirl of this guy, because this is just going to be the trace of the twirl over Rg of order T of rho tensor T, O tensor T. So let's focus on this guy right here. Let's start thinking about some properties of this twirl map, and let's see what can we derive from it with just some very mild assumptions. I'm going to raise this. I hope that's OK. Awesome. So first thing, for convenience, let me just define something that is going to be called the teeth-fold commutant of the group. So this is the set of operators, and let me denote it as com T of Rg. And it's going to be given by the set of operators that are acting on H tensor T, such that A and take U tensor T is equal to 0 for all U belonging to Rg. So it's the set of all the unitaries, all the matrices, not even unitaries, it's all the matrices that commute with U tensor T, right? This is just a very basic definition. If this doesn't make sense right now, we're going to go to some concrete examples about how to compute these guys. So the first question that we can ask is, what happens if I give you an A that belongs to the commutant, and I twirl it? This representation is going to be the bane of my existence. What do you get here? Exactly. You get the same. How do we see this? Let's just explicitly write it out. This is the integral over G of d mu U, U tensor T, A, U dagger tensor T. We haven't done anything. We've just expressed this. But then we said A commutes with U tensor T. So I can just take this out. And I have U tensor T, U dagger tensor T. This is just going to give me identity tensor T. And I get the normalization condition, which we said is one of the fundamental properties. So this is just A. To be a little bit more precise here, this should be, of course, an operator. So we've got this thing right here. So it's kind of nice. If you twirl something in the commutant, you just get itself. That's the first clue as to what the twirl actually does. Then, if I think about composition of channels, which I'm going to denote in this way, what is this going to be equal to? If I take a twirl and I twirl again. Someone, I think? What do you mean same? Right, exactly. So I think that, what's your name? Sorry? Jatel? So what Jatel said was that this should be, if I understand correctly, this. Let's try to prove this. So here we have integral over g d mu v, and here we have v tensor t, and here what are we twirling? We're twirling this twirl, g d mu u of u tensor t. I'm going to think about this as a super operator, u dagger tensor t, v dagger tensor t. Let me put this guy and just get it in here. So this is going to be equal integral of g d mu v integral of g d mu u of v u tensor t v u dagger tensor t. And if we see this and we recall the left and right invariance, this is just equal to this, where we remove and we reabsorb the u, the v, sorry. And now here we just again get normalization. So this is just integral over g of d mu u, u tensor t, u dagger tensor t, which is by definition tau of r g t. And if you have a map or an operator in general that you compose it twice and you get itself, what is this? Exactly. It's a projector. So what we have here is a very important result, which is that the twirl is a projector, and we exactly know where it is that it's projecting, because we've already seen this. If we take something in the commutant, it doesn't do anything. So we can actually be more precise about this, and what we've just essentially shown is that this map takes an operator, and we can refine this equation, and it takes us to the commutant of order t of Rg. So this is great, because now we just need to find, given something, when I twirl it, I know that it's just going to be here. And we just need to look for how, given some operator, it gets mapped into the commutant. So the next thing that I'm going to do, because we've already defined the commutant, let me define a basis of the commutant. So I'm going to define this p mu, where mu goes from 1 to d, where I'm going to find d as the dimension of the commutant. It's not hard to convince yourself that the commutant is a vector space, because given two things in the commutant, I can linearly combine them with any coefficient, and they're still going to satisfy this property. So it is a vector space. It admits a basis. And I'm not going to assume anything about this basis now. I'm not going to assume that it is Hermitian. I'm not going to assume that it is orthonormal. It's just a basis for this space. So it could be completely overcomplete. And we're going to see why this assumption is going to be necessary in a bit. So going here, let's try to go back to what we want to compute. We want to compute this guy for some matrix A. And because it projects into the commutant, we know that we should be able to write this in this way. Right? It's just generic equation that is telling me if this projects into the commutant, this has to be expressed as a linear combination of objects in the commutant with some coefficients that depend on A. Nothing too special here. The question is, how do we get these guys right here? How can we get the coefficients that determine what the action of the twirl is? How would we go about doing this? Let me give you a tip. This is linear algebra. All that we're going to do is multiply matrices and take traces. So how would we go about finding these guys right here? Any idea? Again, all that we'll do is multiply matrices and take traces. This is linear algebra at its more fundamental level. Right? If that would be an orthonormal basis, that would be true. That is correct. But you're going along the right lines, which is we need to somehow find what is the overlap. We know that the trace of A with P news has to somehow come in. So what happens if I multiply left and right by P new dagger? We've multiplied by matrices. The first thing before we take a trace, which is the only other natural operation that we have, is let me write this, and you can let me know if you believe that this is an equality. That I can just take P new and put it inside of the twirl. And that follows from this thing right here. That if you expand this twirl, you're going to get U tensor T, you're going to get A times U tensor T, and you just commute the A right through. So this is an equality. Is this step clear? If not, we can spell it out. Yeah, I see a lot of heads nodding, so I'm going to assume that this is clear. The next thing that I'm going to do on this side, so let me just operate on the left-hand side for a little bit, is what happens if I take the trace of this. Expand this out. Just, if you're using a notepad, I'm going to give you 1 minute to expand this out explicitly, and you can let me know what this is equal to. I think expanding it out is going to make it blatantly obvious. I'm going to take a sip of water in the meantime. I'm sorry? What are those operators, please? They're a basis of the commutant. So the commutant is a subspace of operator space. This guy right here, kind of like, is inside of B of H tensor T. And it's a subspace of the space of operators. Just like before, we drew the space of all operators and we drew a small circle. This is one such small circle. It's just a subspace of the space of operators. And the thing that it has is that because it's a subspace, you can do linear combinations. It's a vector space, and you can define a basis as such. So the P's are just the basis of the commutant. All right. Has someone figured this out? Yes, perfect. This is just a trace of P new dagger A. Is it obvious to everyone? If not, we can explicitly spell this out. Let's write this as the trace of G, D mu U, and we have U tensor T acting on P new dagger A, U dagger tensor T. Let me take the integral outside. This might make things a little bit easier to see. This is the trace of U tensor T, P nu A, U dagger tensor T. And here, you can use cyclical property of the trace, take the U tensor T, get it on the other side. It's going to hit the U dagger tensor T, and this is going to be equal to integral of D mu U of trace P nu A, and we use normalization here. So this is just the trace of P nu and A. So this is great, because we've done a sequence of steps here. We've taken the trace and gotten this. We need to take the trace on the other side. And the ensuing equation is this trace of P nu dagger A is equal to the summation of mu from 1 to D of C mu A, the trace of P nu dagger P mu. And this is fantastic, because the thing that we didn't know how to compute, which was the twirl, is completely gone. And now we have an equation that this we could potentially compute, this we can certainly compute, and we have to just find these guys out. So there's D unknown quantities. We just need to create D such quantities, which should be possible because I just take here new going from 1 to D. So we can now create, I'm going to say do this for all new going from 1 to D. And what you're going to get is a system of equations that is going to look like this. And I'm going to define stuff. So first, let's define this vector, B. And I'm going to swap the order a little bit here, which is the trace of P1 dagger with A, the trace of P2 dagger with A, all the way to the trace of PD dagger with A. I'm going to define C, which is the thing that we want, which is C1 of A, C2 of A, CD of A. And this W matrix, let me just define the mu nth entrance. I think with this definition, let's do it new muth entrance, P nu dagger, P mu. Does this matrix look familiar? What is it? Yes, this is the Gram matrix. We have a vector space, we have a basis. This is simply the Gram matrix for the basis of the commutant. And once we have a linear system of equations, we can solve for C is going to be equal W to the minus 1 times B. And we can now completely find how the Twirl map acts, because we're going to solve for all unknown quantities of how its action is going to look like. So as you can see, we just did a little bit of basic linear algebra, and we've managed to get to this point where we can prove the action of the Twirl. Now, let's try to do this with some specific examples. I think I might be running a little bit behind, but I think this is sufficiently important that I'm happy to stick with this, and we can rush through the practical implementations. So I'm going to get rid of the properties of the Twirl, which I hope everyone has copied, so that we can do a few examples to see how things twirl, because abstract equations are good, but it's always nice to see them in practice. I'm a very visual person, so I need to always kind of like go to some example to make this work. First things first, to try to find things in the commutant, because at the end of the day, all that we required is this, a basis of the commutant. This is the secret sauce. If we manage to get this, we can solve the Twirl. Oh, I forgot to mention something to connect this to the literature. W to the minus 1, people call this the Weingarten matrix. And this is where the name Weingarten calculus comes from. And the whole secret sauce of the Weingarten calculus, which is the ingredient that you need to just make all of this linear algebra work, is finding a basis of the commutant. And this is where a lot of rep theory comes into play, but we're going to see that for some simple examples, we can actually just work them out. So if you now see here in the bottom, I have some tensor representation of matrices. Are people familiar with this kind of stuff? If not, I can explain it, but it's going to make our proofs a little bit easier, and I always like doing proofs by drawing. So if this isn't clear, if you have a matrix A, which we can usually write as summation of ij of aij I j, you can see that this has like an input index I and an output index j. And for people that do tensor network, this might be very similar, very familiar, but you can just write a matrix like this. It's also kind of implicit in quantum circuits, whenever you're drawing quantum circuits, that boxes with legs coming in and legs coming out are matrices. So if you work with quantum circuits, this shouldn't be too bad. We can just label the ith index and the jth index. With this, we can see that if I have two matrices, A times B, what would this look like? We can explicitly write this out, and this is going to be summation of ij of a I k. I want the, let me think about this for a second. I need three indexes. There it is. B, k, j, I, j. So you have two indexes sticking out, I and j, and there is one index that is contracted here, the kth index. In tensor notation, you can represent this in this way. Or here you have the ith output input index, the jth output index, and the kth index is just being contracted with itself. Now, this kind of notation is actually very useful because it also allows us to do stuff like the trace of A, which if we take this thing right here, we just know that this is going to be a summation of I of A, I. And we already know that an index that is contracted that has no free legs is just a loop connecting two boxes. So here, we can just write the trace in this way. Because you're taking the ith and the jth index and making them the same. How do you make the same? By connecting them. So this would be the ith index that is contracted. There is no free legs. This is a scalar. It's not a matrix. Some very natural properties follow from this. So the identity, we usually write it summation of I, no coefficients in front. This we usually write as a line. And this is also really nice because we know that the trace of the identity, if I define D as the dimension of my Hilbert space, we know that this should be equal to D. But we already know that doing a trace means connecting indexes. So actually, let me put this here as a line. And this tells me that I connect a line with itself. I get a loop. This is equal to D. So this is going to be the basics of how to do Weingarten calculus with tensor notation. I put some other stuff here. We're going to get to those in a second. If we have time, I was also planning to talk about orthogonal group, but I don't think we're going to get there. But let's keep this in mind. So consider a specific example, which is going to be, let's take G to be the whole unitary group. So I'm going to get rid of all of this. And let's consider the case where G is UD. I give you a group. I need to give you a vector space where this is acting. So let's take the vector space as the Hilbert space and take the representation of U belonging to G to just be U. So single unitaries, right? And we want to try to find what are all the matrices that are going to commute with the unitaries. So these are D times D dimensional unitaries, and I want to try to find all the D times D dimensional matrices that commute with the unitaries. This, you can write it in this way. This is equivalent, these two. And I kind of like this because in diagrammatic notation, this just means that I have a U, I have an A, I have a U dagger, and I want somehow this to be equal to A. What can I put in here? One way in which I like to think about this problem is if I have U's and U daggers, and this needs to be true for all unitaries, probably the only way to do this is to get somehow this U to connect with this U dagger and kind of have them annihilate each other. That way they will disappear from the diagram. So how can I do this? What do I have to put in A for this to happen? Yes, if I take A to be the identity, well, let's do it like this. These two will just come together. They'll become an identity, and this will just be equal to this, which is what we wanted because the identity was technically here. So yes, the identity commutes with all the matrices, all the unitary matrices. You can try to think about this for a little bit longer and try to see if you can find out if there's any other unitary that will commute with everyone, but I can now say that there isn't. If you know some representation theory, this is a consequence of Schur's lemma that tells you that this group is irreducibly represented in this vector space, so the commutant needs to be one-dimensional. So there's only one thing in the commutant, and that is the identity. So, right, this tells us that in this case, the basis is just the identity. Now, let's do Weingarten calculus. How do we need to construct the gram matrix, which is now going to be a 1 times 1 matrix, whose sole entry is a trace of identity times identity, which is just D. So W to the minus 1 is going to be 1 over D. Very easy matrix to invert. Now, if we go about trying to solve that problem, C equals W to the minus 1 times B, you can see that the twirl of order 1 of the unitary group of a matrix A is going to be 1 over D, the trace of A times identity, identity. It's just one step of implementing that equation right there. So this is kind of very nice because I can just simplify the notation a little bit. And it's very explicit that the twirl is taking a matrix and projecting into identity, right? So we've already got the first order twirl. What if we now do the second order twirl? And let me get rid of this because it's up there. So I don't think there's a lot of issue erasing this. What happens if I give you the group is still UD? I give you now the vector space is H tensor 2. And the representation acting on this space is U tensor 2. And now I need to find all the matrices that commute with U tensor 2. What can we do here? Yes, the swap actually works. If we put here a swap, which is just literally swapping the Hilbert spaces, this is equal to itself. Of course, we have the identity, so we could have put here 2 straight lines. And this is going to be equal to this, or of course, U dagger, U dagger. You can wonder if there is more stuff. I'm going to save you some time, and I'm going to tell you that there isn't any more stuff. So here, the commutant is 2-dimensional. It's spanned by identity, tensor identity. Or remember, this is identity, tensor identity, and swap. Now we can build the Weingarten matrix. And here we need to put the trace of identity times identity. And sorry, identity tensor 2 times identity tensor 2. This should give me this squared, because I have this. And you can also think about it in this way. We already said each loop is D, so this is D squared. What is the trace of swap with itself? Multiply swap by itself, take the trace, which means close the loops. How many loops do we have here? Yes. So here we get a D squared, which is the trace of swap times swap, which we actually know that swap is its own inverse, so this should be the trace of identity tensor identity. What happens if I want to compute the trace of identity tensor identity times swap? Are you sure? Let's do it. There's only one loop. So this is equal to this, which is equal to D. So the gram matrix looks like this. And the inverse is going to look like 1 over D squared minus 1, 1 minus 1 over D, minus 1 over D, 1. There is absolutely zero way that I can invert a 2 times 2 matrix, even if my life depended on it. So I just did this, and I've done it so many times that I kind of just remember it by heart. So yeah, this is what you would get with this inverse. And how would that look if you twirl an operator? Let me actually write it here so that I don't have to erase. The second order twirl over the unitary group of a matrix A is going to be 1 D squared minus 1, the trace of A times identity tensor identity minus the trace of A times swap over D identity tensor identity plus 1 over D squared minus 1, the trace of A times swap minus trace of A identity tensor identity, which this is just, of course, the trace of A, divided by D component into swap. And that's it. You've done the second order twirl. If you start seeing the pattern here, it might become obvious. What happens if I give you T copies of the identity group? So now I ask the question, let me erase this. What happens if I give you here what are all the things that are going to be in the commutant? Maybe you can spot it. What did we do with identity and swap? We found ways to connect a U with a U dagger so that they annihilated each other. So I could have drawn like this connected to here, this connected to here. This is just a straight line. This kind of goes here, this kind of goes here. What does this right here look like? It's just a permutation. It's just a permutation of an element, of T elements. I have T elements on the right, T elements on the left, and I need to connect them one by one. So this is kind of nice because it's a result, a really well-known result and famous in representation theory that tells you that the T-fold commutant of the unitary group is going to be spanned by some representation of the symmetric group ST. And what is the representation? The representation that swaps qubits. So this is just, if you wanted to expand this to higher orders, this is the recipe of how to do this. And this is a one-to-one correspondence. OK, what can we use this for? If you wanted to take this, and you wanted to, for instance, ask the question, let me now go to this one, so that it's very non-linear, my writing process. I realize I'm just like jumping all over the place. What can we use this practically for? Just this equation that we've derived, the first and the second order twirl. Let's assume that now you have a very deep quantum circuit that you're going to try to train. So this has a lot of gates, a lot of entangling gates, and you're going to be making some measurements. And you're going to try to compute something that looks like the trace of U rho U dagger O. And now, if this circuit is very deep, it's sufficiently deep that whenever I sample parameters and I initialize it, I can say this is going to be equivalent to sampling unitaries from the unitary group. And you might talk about designs, which are sets of unitaries that match moments of the unitary group. But for now, let us just assume that I have a circuit that whenever I sample parameters, when I randomly initialize it, it's almost as if I were sampling unitaries from the unitary groups. And I want to know if this loss function is going to concentrate. So I take this, and I want to compute the variance. And we already know that this required the computation of the first moment, which was this. But now we can just use the equation that we have right here. If we replace it here, this is just going to be equal to, let me actually rewrite the equation that we had, which was twirl G of order 1 of rho O. So I can just replace this by what we already have. And this is going to be the trace of rho divided by D, which is this first guy right here, times identity. So I get the trace of identity O, which is just the trace of O. And if we're measuring a Pauli expectation value, this is just 0, right? So we've managed to find the first moment, not too interesting. We now need the second moment. I now need to compute EU of trace U rho U dagger O squared, which we've already seen that this is the trace of tau G2 rho tensor 2 O tensor 2. And let's use this equation that we have right here and just explicitly write this out. This is going to be 1 over d squared minus 1. We have the trace of rho tensor rho, which I'm already going to write as the trace of rho squared, minus the trace of rho tensor 2 swap. Sorry, this is the trace of rho squared, which is equal to 1. And I have here divided by d. And people can see that this is just the purity of rho divided by d. And then I'm going to have here the trace of identity tensor identity O tensor 2, which if O is a Pauli, this is 0. So this whole term, the first term, is going to contribute nothing. But the second term, we get 1 over d squared minus 1. This is going to look like the trace of rho squared minus 1 over d. And I have here the trace of O tensor 2 swap, which is nothing more than the trace of O squared. If O is a Pauli, O squared is identity. So this is just going to give me d. Putting everything together, what we find is that the expectation value of the unitary group of the trace of U rho U dagger O squared is equal to d divided d squared plus 1, sorry, minus 1, the trace of rho squared minus 1 over d. So the variance, which is exactly equal to this minus this squared, is just d divided d squared minus 1, trace of rho squared minus 1 over d. What can we say about this variance? How does it scale with the dimension of the Hilbert space? Yeah. It scales, it goes to 0, but how does it go to 0? It goes to 0 like one of the dimension of the Hilbert space, because this guy right here can be at most 1. So you can see that this guy belongs to order 1 over d. So this thing that we've just done is, if you're familiar with Jared McLean's paper, Barren Plateaus in Quantum Neural Network, the first paper that proved Barren Plateaus, is this. This right here is a Nature's Communication paper that has like 2,000 citations, and it's just this math. So you can see that it's a very powerful tool. You can use it to prove Barren Plateaus results very, very easily. I have 20 minutes left, so I'm going to try to rush into how can we use this for quantum convolutional neural networks, because we've gone quite a long way. But before I move on, I always want to give some references. If you want to learn more about the Weingarten calculus, there is this really nice tutorial by Antonio Anamele. This is the reference that I would give. It's a really nice paper. It contains a lot of the details here and so much more. If you want to check the reference for the paper that proved the barren plateau paper, the Google paper is this one right here. They use kind of like a little bit older language of Weingarten matrix theory, but it's more or less the same calculations. Okay, how can we use all of this for quantum convolutional neural networks? And I don't think I have anywhere near enough time to try to do the whole proof. So I'm just going to give you the basic ideas. So we said that our architecture was looking, let me define a quantum convolutional neural network on a couple of qubits. Maybe you do this. Then you trace out this qubit, you trace out this qubit. You get these two right here, and here you make measurements. So if you want to use the Weingarten calculus, the first thing you need to do is assume that something is hard random over something. So how would we go about doing that? This circuit is definitely not going to be hard random over the whole unitary group. It's logarithmic depth, it's fairly shallow. This is not going to be a good representation of this circuit. But what you can say is, let me assume that each one of these gates is going to be themselves sampled from the unitary group, in this case, acting on 4 qubits. So this is the assumption that I'm going to make. I'm going to take these gates, and I'm going to assume whenever I randomly initialize my circuit, this gate is sampled from U4, this gate is independently, and identically sampled from U4, this, and this, and this. So now you can use the power of the Weingarten calculus, not for the whole unitary, but for these guys right here locally. And in this case, it's quite convenient to work in the vectorization picture to try to understand, to try to do the calculations, but I don't think I have enough time to go through that. So I'm actually happy to chat with people a little bit more about how to go from this assumption for the proof. It's maybe like 30 more minutes, but I don't want to keep people away from the coffee break. So let me just say that what you can actually do is you can ask the question of, if I Heisenberg evolve a measurement operator with a QCNN, and I assume that each one of the gates in this QCNN, so now I'm going to put an UI, where this is U1, this right here is U2, this right here is U3, this right here is U4. If every U1 is sampled from U4, we can now compute this guy. Using exactly the same tricks that we do, it's just a little bit harder because it's just local Weingarten calculus, but morally is going to be pretty much everything that we've done here. So this is actually going to tell us how is this operator going to be expressed in terms of things in the commutant. The notion of commutant is a little bit weirder, but we can actually get this expression because this is what Weingarten tells us. You take something, you twirl, and you get an expression in terms of operators. So this is what we do here. And now we can ask the question, how does this guy scale right here? Are there terms that decay exponentially? Or are there terms that decay polynomially? And what you will find is that if you expand this in the Pauli basis, you're going to find that here I have a coefficient Cp, where P belongs to the Pauli basis, so identity x, y, z, tensor n. What you're going to see is that the magnitude of these coefficients, they're going to decay as 1 over 2 to the bodiness of P. And this you can prove rigorously and analytically. So what does this mean? That whenever I Heisenberg evolve my measurement operator, and I compute the expectation value, this is essentially only going to be composed of local Paulis. All the global Paulis are going to decay exponentially, and they're not going to be contributing. So this doesn't really live in one closed subspace of BH like we used to have before. It's not like whenever I Heisenberg evolve my measurement operator, I can just stay in a small subspace. I can go everywhere. And we should be able to go everywhere because the QCNN contains all the qubits in the line code. So I should be able to transform a local Pauli into a global Pauli. But in average, what happens is that the space of local Paulis contains most of the weight, and then it just decays exponentially. So we can say, OK, maybe when QCNNs are randomly initialized, they mostly just live here. And what happens if I just simulate this subspace right here? Can I see that I can train a model by just looking at this subspace, and it will perform as well as the QCNN? So let me get to that. Here are some commutants. For the unitary group, it's just permutations. For the orthogonal group, you get kind of like Bell states in the Brouwer algebra. We can chat more about this. These are the analytical results. These guys right here is just magnitude of the coefficients in the Pauli as a function of the Pauli weight. And this is like a very beautiful exponential decay. We can predict this curve using Weingarten calculus. So this is what I told you. Just wanted to say that you can rigorously prove. So how do we simulate QCNNs? We already know that whenever they're randomly initialized, they can only look at the information that is encoded locally in the states, because this is where the Heisenberg evolve operator is going to look like. And you could argue, sure, maybe QCNNs are easy to simulate when they're randomly initialized. And as a matter of fact, they are. You just do kind of like this backwards propagated Pauli from our paper with Zoe and Robert Huang, and it's actually going to work. But you might say, maybe during training, the QCNN looks at the information that is encoded locally in their input states, and then kind of just goes somewhere else. And this might go into a region of the landscape that is not classically simulable. So let's just try to do it. Let's just take a QCNN and truncate all the high-weight Paulis and just look at the information that is encoded locally in the input states. So now we need to find a description of the input states in this subspace. All of this first part of the talk was to determine the invariant subspace that we should be looking at. And remember, the second step is find a description of your states in this subspace. How can I get an efficient description of a quantum state in local Paulis? Just classical shadows. This is standard. So what we did was, we can't rigorously prove that the optimization is not going to leave the classically simulable part of the landscape. But let's just do proof by construction. We're just going to take all the problems where people have used QCNNs in the literature and show that by just looking at the observables locally and just looking at the QCNN action there, we can solve the optimization task. So this is our third notion of classical simulability. So we've done this for quantum data. We've taken classical shadows for systems of 1,024 qubits. This is the bond alternating model. It has a trivial and a topologically protected phase. With only taking 250 shadows and about 60 training points, we can classify on 1,024 qubits to almost perfect classification. We can also do multi-class classification, like on the Haldane chain for 512 qubits. It works really well. We can also do the NNI model, which has 4 phases, or the cluster model, which has 4 phases. We see that these guys are good classifications. These are errors. The crosses are training points. As you decrease the number of training points, your errors increase, as expected. But what's interesting is that with this method, we have actually found much better results than what we did with training the QCNN. And then this has been like systematic. Then when we do classical data, we can do the whole thing again. We can simulate. We can do angle encoding, amplitude encoding. We can do different types of angle encoding, benchmarking. And in all of those, it's comparable or higher than quantum, that full QCNN simulation. And here's a little bit of a rant, which is that the hope is that we can use the quantum computer just to get the shadows. And then there's still a quantum component in our data. The thing is that for classical data, even the encoding part is classically simulable. So here, there is absolutely nothing quantum. We don't need quantum computers for shadows. We don't need anything. So I really have a hard time to understand why you would put classical data in a QCNN, because the whole pipeline is classically simulable now. And it works. It just works like extremely, extremely well. So the other thing is that people are trying to use QCNNs for classical image classification, and we have classical methods that work extremely well. So if you want to put them in a quantum computer, I want to hear like a really great motivation. And again, I'm not saying that there is no reason to use quantum computers for classical data. I'm just saying that maybe we should be smart about what it is that we're doing and have really good reasons. Because remember, I'm playing devil's advocate here. My talk is trying to tell you, don't do this, but I actually think that quantum computers can work in some cases. We just need to be careful about what it is that we do. The other thing that I have a very big issue, and this is for practitioners, if you have very big classical data, we can't simulate very big quantum computers. So how are we putting our data inside of the quantum computer? You have to do some dimensionality reduction first. Are you doing PCA? Are you first running your data to something that is doing a lot of pre-processing, and then the quantum computer is getting a problem that is essentially solved? If you put PCA into a quantum computer, PCA solved the classification problem then. The first three components of PCA and MNIST have all the information to classify anything. So, you give those to pretty much anyone, and they can classify. So I don't think quantum is doing anything. I think in that case, PCA is doing something. So this is just a mini rant for my own sanity about the use of classical data and quantum machine learning. But going back to QCNNs, what did we show? That QCNNs have been successful in the literature because they're trained on very easy data sets that can be just classified by looking at information locally. This is, for me, particularly interesting for quantum data because it tells us that all the information that is needed to do classification of quantum states is kind of like locally encoded. And probably you don't need all of this machinery. You can just measure a single qubit for most of those models, and you can do perfect classification without training parameterized quantum circuits and whatnot. And even if we say maybe we need topological data, that it doesn't look locally mixed, the problem is that we're trying to classify topological data with trivial data. So some state that is very complicated and some state that is fully aligned. What is hard is classifying topological order. But telling these two apart is very easy. I just check one qubit, and if it's pointing up, it's not topological order. So it's a trivial classification task. So this is also to say that I think that quantum machine learning for quantum data is going to be very useful, but also we need to make sure that we're benchmarking in problems that are hard, not problems that are trivially easy by just measuring one qubit. So this is also something that I think it's important for us to keep in mind as practitioners whenever we want to claim that quantum models are doing something useful. And then because we have locally easy data sets, we can just do classical shadow and simulate the QCNN effectively. So I'm sorry that we didn't get a chance to do all the details here, but this is a little bit of how one can dequantize QCNNs by just starting with Weingarten calculus and identifying this subspace right here. So to start wrapping up in the last 5 minutes, I want to do a brief recap of the last 3 talks and what it is that we've done. So the first thing is that we look at all of those barren plateau free techniques and architectures. In each case, we identified the polynomial subspace where our data lived. That can be a strict subspace, as it was the case in Lie algebraic techniques, or it can be an effective subspace where most of the time you live here, and then the rest just kind of decays exponentially. We found a way to represent the action of our unitary in that space. That could be via the adjoint representation or this Pauli weight truncated simulation methods. And we try to find if there was a way to try to get the data, how the data looks in this subspace, usually via some shadow tomographic technique that is efficient. And for me is that for most cases, quantum computers are still needed, but we don't need to run a circuit on a quantum computer. And this is going to be extremely, extremely important. So this is kind of like when I talk about dequantization, these are the things that I've been talking about. Now, there are a ton of holes and caveats of all the things that I've said, all of these big claims of quantum machine learning is not going to work, and I'm going to address them. Because I don't want to tell people don't do QML. There is a lot of caveats, and more importantly, a lot of really interesting research questions that are open. So what are the caveats in our arguments? Again, we are not saying that if some expectation value is not exponentially concentrated, then it's not classically simulable. We know that this is not the case. We've already gone ahead of the curve, and we've shown this ourselves with Shor's algorithm. So we're not saying that, so don't take that message away. The problem is that those examples don't really resemble how we train models. What are the type of circuits that we use for training? And we don't know if they're going to be useful. They kind of just break our initial assumption of that the problem of quantum machine learning is this exponentially large feature space, because it's not like quantum algorithms cannot navigate this exponentially large feature space. In fact, We have algorithms that do them all the time, Grover's algorithms, Shor's algorithms. They operate in this exponentially large space, but they do it in a very orderly and purpose manner, where every single gate has a purpose, and they work in tandem. And Scott Aronson says this thing that I really like, which is that quantum algorithms work by carefully choreographing the patterns of constructive and destructive inferences in your interferences in your outcomes. So if we don't do this carefully, yes, quantum systems and their Hilbert space can be a problem. So a lot of the things that we've done here, we rely on the proof of absence of barren plateaus. So this is essentially the proof of absence of barren plateaus. You have some components in your variance that are polynomially vanishing, hence the variance is polynomially vanishing. And this is what actually relied us to get the subspace that we need to simulate. You could potentially find heuristically some ways to get large gradients, and we don't know what the subspace is. And I don't know if this is going to be classically simulable. And this is the whole idea of warm starts and smart initializations. Are those somehow special? Because this is very important to note. A barren plateau that has a landscape that has a barren plateau is a probabilistic statement. This means that in most of the landscape, you're going to be flat. But you can have many pockets of well-behaved landscape. And this is what smart initialization schemes do. Now, are those useful? Can we find the right initialization strategy? I think that we might be pushing the complexity somewhere else, and I have this gut feeling that there needs to be a low conservation of complexity. We can't just solve our problems by getting rid of all the complexity of training in an exponentially large space. So we have some results that we're hoping to put out soon, where people are excited because they find one smart initialization technique. They're like, oh, I found this initialization technique, now I can have large gradients. And I was like, why is this initialization technique so special? But what we've been able to prove is that there's like whole continuous, exponentially many families of smart initializations. Do they all connect to the global minima? I hardly think so. So I think we're trading the problem of how to like randomly initialize sufficiently close to now you have exponentially many families of smart initializations to check, and now this is where your complexity is going to be at. And we haven't even talked about local minima. So that is a whole new thing. So I don't know if warm starts are the solution to all of our problems. All that I'm sure is that any form of meaningful quantum advantage will necessitate warm starts and smart initializations. We have some types of generative models that don't fit this framework. They're not based on computing this sort of expectation values. So this is also something to take in mind, because the scaling of sampling and computing expectation values is very different. What are the new opportunities that follow from here? Quantum computers are still needed. Also, just because you can simulate a quantum model doesn't mean that you have to or that it's efficient to do so. Which one is there more efficient? Is there still some polynomial advantage in running some classically simulable model? We don't know. I think this is a very interesting question. And maybe there's some polynomial advantage in this case. For me, these type of dequantization algorithms, they're more near-term because we don't have to run parameterized quantum circuits. We just need to run the circuits that prepare data and do some tomographic measures. So I personally really like this. So maybe we can push some form of quantum advantage even closer by getting more computational complexity onto quantum devices. What happens if we have a model that we train on a quantum computer, on a classical computer, but then deploy in a quantum device? Can we also use this to reduce the number of times that we need to call our quantum computer? What about quantum machine learning for metrological problems or sensing? We don't care about computational advantage there, so I cannot take a classical simulation and put it out there to measure a magnetic field. So maybe I can take a model that is classically simulable, train it classically, deploy it quantumly. So this could actually be very useful for metrology and sensing, where advantage has a completely different meaning. Again, there is no one simulation algorithm to rule them all. We just saw that HVA and QCNN have two completely different simulation algorithms. And can we find new quantum-inspired classical methods? What are going to be the resources? How can we make something that is simulable less simulable while still being useful? Those are questions that I care for. And of course, what is the role of data? And this idea of BPP-SAMP that we've talked about. So, and even once we extract the data, I give you those shadows. We've been actually simulating the action of the QCNN as a sort of quasi-unitary map. But you don't have to do that. You can take your classical data and just put it somewhere else. And maybe that's more efficient. So to finish, if someone asks me, should I do quantum machine learning? My answer would be no, but yes. And yes, but also no. I think it's a complicated question. For me, quantum machine learning is not classical machine learning, and I don't think it's ever going to be, in the sense that it's not going to be a tool where we can pick our favorite problem and put it in here. I wish I had more practical tools to give you on how to solve the problems that you're interested in. But as I said, I think we're trying to reach a quantum advantage by process of elimination. Like, don't do this, don't do this. Maybe let's go in this direction instead of this. And trying to have a more honest approach. This is close to my heart. If you want to use QML for classical data, what is the quantum property that you expect is going to give you a quantum advantage? Like, why does Shor algorithm work? What is the structure in our data that makes Shor algorithms work? There's like a very strong group theoretical properties in the hidden subgroup problem that makes quantum algorithms work really well for factoring. So there is an underlying reason why to factor on quantum computers. This idea of we're trying to get rid of regions where we can't get a quantum advantage, I think this is something that I've already said quite a bit. How can we get high quality data that is efficient? I think that this is a problem that I'm personally very interested in. So I think that quantum machine learning for data extraction is a very important problem. And for me, I think that I'm going to keep working on quantum machine learning. I really like this field. I think there's a lot of interesting problems. I just want to try to do this in a more like theoretically based approach. And how can we bring classical near-term quantum machine learning and fault-tolerant quantum machine learning closer? Maybe this is something that you really haven't thought, but if you have a fault-tolerant quantum computer, would you just implement VQE? Does that mean, oh, you're going to have VQE but with no noise? Well, I don't know, because VQE requires small angle rotations. And fault-tolerant quantum computers are not great at that. Fault-tolerant quantum computers can do Clifford gates and T-gates. Let's assume that this is the framework of our free and resourceful gates. And if you want to compile a very small angle rotation, just a single gate is going to require a massive amount of T-gates. So what is quantum machine learning going to look like in the fault-tolerant era? I think it's a massively unexplored area. And for you that are students, or what is the advice that I would give from my own personal experience, is that if you want to do quantum machine learning, yes, absolutely do it. For me, working in this field over the past 7 years has been a really great way to learn a lot of topics that have been really useful. I've learned a lot of quantum information, like entanglement measures, trying to model quantum channels to understand noise, advanced mathematical tools. I highlight Cauchy-Schwarz inequality because I think a third of my proofs is just let's apply Cauchy-Schwarz inequality until we get somewhere. But we've seen representation theory, random matrix. I've also been learning about fault-tolerant quantum computing. I'm not an expert there, but I'm definitely willing and trying to learn. Understanding complexity theory. Why is BQP different than BPP? I think this is going to be important. And for me, if you get all of those solid background while learning quantum machine learning, this is going to be more important than being stuck in hyperparameter hell trying to train a parameterized circuit. Like, I'm not saying don't do that. I'm saying do that, but get this healthy dose of more solid knowledge that you can take pretty much anywhere after you finish that paper on QML. And the final thing, which I think is important, this is from Maria's Schuld paper, The Subtle Art of Benchmarking Quantum Machine Learning Models, is be careful about positive bias. When you set out to use quantum machine learning for a problem, are you trying to prove that there's going to be a quantum advantage, or are you honestly trying to see if there could be a quantum advantage? I've recently seen 2 papers in the past like 3 months. One of them is QAOA, the other one is VQE, and they're like saying we do big benchmarkings, we can find an advantage. And I was like, whoa, this is so refreshing. Like, you have 300 papers saying quantum advantage, and then 2 papers saying we did all of this, we couldn't beat state-of-the-art methods. So, you know, I think there's a lot of positive bias out there, and we should be very conscious and careful about that. And I know I've gone long enough, so just to finish, I would like to say that LANL has a quantum computing summer school. Our applications are going to be opening soon. As just like Daniel, I do want to say that our acceptance rate is about 3%. We get about 700 applications, and we can only take 20 because this is a 10-week-long internship program where students are paired with Lanol mentors to work on research programs. So it's not classes, it's just research. It's let's do research for 10 weeks. We do bring speakers. We also have some classes, but it's mostly a 10-week-long research program. Also, we're usually looking for students to do internship with us, with postdocs. Even if we don't have an ad out, just always shoot us an email. You know, the worst thing that can happen is we tell you, at this point, we don't really have an opening, we're waiting for funding or something like that, but we're gonna keep you in our mind. So we're always looking for great people to work with. And with that, I wanna thank you all for your attention. And I can take questions afterwards. I think we've gone long enough into the coffee break.